It's time for Maths with Mr. Thomas.
Hello, Lark's Academy. Chapter 12, lesson number 2, moving on to look at polynomial equations. Now, polynomial equation is going to be something of the form, your z cubed take away 4z squared plus 9z take away 10 equals 0. And you know we can go on and find the roots of that because we did it in higher. So with this first example, verify that z equals 2 as a root of that equation. Well, that's something we already know how to do. And then find all the roots of the equation. Again, is kind of something that we know how to do. However, it's coming into this chapter on complex numbers. So let's keep going and let's see if it gets any trickier. So using our higher maths, well, how would we verify that z equals 2 is going to be a root of that equation? Perfect. What you could do is you could replace z with 2. So work out 2 cubed, take away 4 times 2 squared, plus 9 times 2, take away 10 equals 0. And what we should get is 0 equals 0. And if it does, woo! It means that z equals 2 is going to be a root. However, because we're asked to then go on and find the other roots, well, we need to somehow factorize it. So what I'm going to use instead is synthetic division from higher, which is when we use our L-shaped table. So, if f of z equals z cubed take away 4z squared plus 9z take away 10, well, we know when we're setting this out with our synthetic division, we would take the coefficients of z cubed, z squared, all the way down to just this number on the end. So the coefficients we would have would be 1 because it's 1z cubed. Z squareds, we've got negative 4. Z's, we've got 9. And the number on the end is negative 10. So that's us writing the coefficients. We want to verify that z equals 2 is going to be a root. So just to the left-hand side of the table, we will have 2. Woo! We then want to work our way along using synthetic division from higher. Maria, how well do you remember it? Very well. Perfect. Then let's go, Maria. So you're wanting to bring this 1 down. 1 times 2. 2. After that, you want to add these numbers together. So negative 4 add 2 will give you negative 2. Again, multiply by the 2. So 2 times negative 2. Negative 4. Brilliant. 9 add negative 4, or 9 take away 4, would give you 5. And after that, again, you're multiplying by the 2. So 2 times 5, 10. Brilliant. Negative 10 add 10 would give us 0. Fantastic. And because we've got this 0, it means our remainder is 0. And because the remainder is 0, Mrs. Galbraith, what does that mean? Perfect. It means that z equals 2 is a root of that equation. Woo! So, we've done the first bit. We've verified that z equals 2 is a root. Again, you could also have subbed 2 into this equation. That would also have worked. However, what we want to do then is discover the other roots of the equation. And in order to do that, we've got to factorize this equation. So, by factorizing, the polynomial can now be factorized, we can say that f of z, if f of z was equal to just this left-hand side, we could say that that would be equal to, because we've got a 2 here, well, you know that that is going to be a root, so the factor would be z take away 2. And with the other bracket, you get the coefficients just from the denominator down here, as I'm sure you remember from higher. So because this up here was z cubed, its coefficient is z cubed, if we take 1 off the power, this will be the coefficient of z squared. So we would have 1z squared. Working our way along, well, if that's z squared, this will be the coefficient of z, so we would have take away 2z. And our 5 would just be the number on the end. Because it's a positive 5, it would be plus 5. So, factorising, we've got f of z equals z take away 2, and then brackets z squared take away 2z plus 5. We know that the first root was 2, but the other roots are going to come from this part here. This is where we get the other roots from. So what would we have to do with that? Perfect. We would have to factorise. So if we factorise that, what would we end up getting? I don't know. Perfect. Because we can't factorise that. And if we can't factorise it, what would we have to use? Lewis! Brilliant. You would have to use the quadratic formula. Boom, boom, boom. And with your quadratic formula, you want to take the coefficients of your z squared and z and this number on the end, and they would be the values of a, b, and c. So, using the quadratic formula with a equal 1, b equals -2, and c equals 5, let's go over the page and do that. Quadratic formula, we're wanting to find out what z is, so it's z equals -b plus or minus the square root of b squared minus c, 4ac, over 2a. Sub those values in for a, b, and c. Remember, a was 1, b was -2, and c was 5. Sub them in, and this is what you get. And if you simplify this bit here under the square root, simplify the b squared minus 4ac, we end up getting 2 plus or minus the square root of -16 over 2. Ah! We have the square root of a negative! Dun dun dun! But because we have just worked through that first lesson with the introduction and complex numbers, we know how to deal with that. If you end up getting the square root of a negative, what you can do is you can imagine that as the square root of 16 times -1. And you could split that up, so it's the square root of 16 times the square root of -1. The square root of 16 is 4, and the square root of -1 is I. Perfect. I for imaginary numbers. So that would become 2 plus or minus square root of 16 is 4, but because it's a negative, square root of -1 is I, so it's going to be 2 plus or minus 4i over 2. Because we have that, we can divide the 2 by 2 and 4i by 2, giving us then 1 plus or minus 2i. Woo! And we can say, therefore then, that our roots are, well, right away we had at the start z equals 2. That was our first root. And for the other roots, well, we have z equals 1 plus 2i. And we also have z equals 1 take away 2i. So that would be all 3 roots of that equation. Yeah. What do you notice about this? What do you notice with the roots? Perfect. If you've got z equals the 1 plus 2i as a root, we've also got the complex conjugate. Remember, the complex conjugate is when you change the sign for the imaginary part. So the 1 take away 2i would also be a root. And that is true whenever you have a polynomial with real coefficients. The roots of the equation f of z equals 0 always occur in conjugate pairs, meaning then that if z equals a as a root, well, z equals a bar, the complex conjugate, will also be a root. So let's use that information to try a slightly trickier example. Let's move on to example 2. Example 2, part A. Verify that z equals 1 plus 2i as a root of the equation. Z to the power of 4, take away 6z cubed, plus 18z squared, take away 30z, plus 25 equals 0. Part B, write down another root of the equation. And part C, find all the roots of the equation. Woo! They're spoiling us. So with the first example, what I used was synthetic division to work this out. Except because I've got a complex number here, it's maybe easier to substitute in. So I know that z is equal to the 1 plus 2i. What I'm going to do is I'm going to work out what z squared is, what z cubed is, what z to the power of 4 is, and sub them in. So we already know that z is equal to the 1 plus 2i. Let's work out z squared. We know z squared is just going to be z times z, so it'll be the 1 plus 2i times the 1 plus 2i. If you multiply out the brackets there, we'd have the 1 times the 1, which is 1. You'd have 1 times 2i, which is plus 2i. You'd have another plus 2i, which is plus 4i. And you'd have the plus 4i squared. Remember, I squared is equal to -1. Brilliant. So replace I squared with -1, meaning then we'd have 1 plus 4i, and then 4 times -1 would give us take away 4. Simplify this, so you're gathering the real part and the imaginary part, so 1 take away 4 is -3, and the imaginary part, we'd have the plus 4i. That's z squared. Let's now go on and work out z cubed. So z cubed will be z times z squared, which will be the 1 plus 2i times this -3 add 4i. Multiply the brackets once again, so 1 times -3 is -3, we'd have a plus 4i, take away 6i is -2i, and multiply the 2i by the 4i, we get plus 8i squared. I squared is -1, so you'd have 8 times -1, so that would then become take away 8. Gather the real parts, gather imaginary parts, so -3 take away 8 would give us -11, and the imaginary part, we'll get this -2i. Z to the power of 4, we need that as well. So z to the power of 4, you could work out this different ways. You could just do z squared times z squared, or you could do z times z cubed. I'm using z times z cubed. So the 1 plus 2i times by this negative 11 take away 2i. Multiply out the brackets there, that would give us negative 11. We would have take away 2i, take away 22i, which is take away 24i, and that would be take away 4i squared. I squared is negative 1, so that would be negative 4 times negative 1, which would give us plus 4 on the end. Gather the real parts and the imaginary parts, so negative 11 add 4 is negative 7, and it's take away 24i. Because we now know z to the power of 4, 3, 2, and 1, we can sub them in up here in our equation. So that's the equation. Replace the z to the power of 4 with negative 7 take away 24i. Replace the z cubed with the negative 11 take away 2i. Replace the z squared as well with what that is, and replace z with what that is as well. From here, if you then multiply out the brackets, you would get the negative 7, take away 24i, plus 66, plus 12i, take away 54, add 72i, take away 30, take away 60i, plus 25. And that would simplify to b. What would you get for the real parts if you're adding all the numbers without the i's? What do you end up getting, Lauren? Perfect, you would end up getting 0. And with the i's, if you add all of them together, you would also get 0. So we get 0 plus 0i. And to simplify, 0 add 0i. What's that just the same as? Good, that would just be the same as 0. Well done. And because we're getting out 0, well, you know when you are subbing in the root into the equation and you end up getting 0 equals 0, well, it means then that that would be a root of the equation. Perfect. Part B, write down another root of the equation. How would you go about doing this? James, what do you do? Good, because we know that z equals 1 plus 2i as a root. Well, 1 plus 2i is a complex number. There's a real part and an imaginary part. And because we've got the polynomial with real coefficients, you can see that as real numbers for the coefficients, it means the complex conjugate would also be a root. And the complex conjugate of the 1 plus 2i would be 1 take away 2i. Brilliant. So you know 1 take away 2i would also be a root. Woo! So we've got this first root and you've got the second by taking the complex conjugate. Fantastic. For part C, find all the roots of the equation. How do we go about doing that? Well, what we need to do is, similar to that first example, we need to take this up here, we need to take this equation and we need to factorize the left-hand side. We know that what we've got is these two roots. We've got the 1 plus 2i and we've got the 1 take away 2i. So we need to go on and we need to think about the factors. So, moving on, this is what we had. F of z equals, we've got our z to the power of 4, take away 6z cubed, plus 18z squared, take away 30z plus 25. And remember that z equals a. If that is going to be a root, then what you'll have is z take away a in brackets as a factor. So for example, imagine if you had z equals 2 as a root. Well, in the brackets you would have z take away 2 as a factor. If you had z equals negative 7 as a root, well, you'd have z plus 7 as a factor. So if you've got the roots, you're going to have the z take away that as a factor. Because we know two of those roots, we can find two factors. So the roots we had were z equals 1 plus 2i and z equals 1 take away 2i. So a factor then, well, the factor is when you would have z take away that and you would get it equal to 0. So really what we've got is you would have z take away that 1 plus 2i. And for another factor, you would have the z take away that 1 take away 2i. So they would both be factors. What we can do with them, because they are both factors, we could multiply them together in order to find a larger quadratic factor. So let's do that. So let's take those two factors, the z take away the 1 plus 2i and the z take away the 1 take away 2i, and multiply them together. However, to multiply them together, what we want to do is we want to take the real parts, put them together, and the imaginary parts and put them together in the first set of curly brackets, and the same for the second set of curly brackets. So the real parts over here we've got are the bits without any i's, so we've got the z take away 1. So you can say z take away 1 would be the real part, and if you multiply the brackets you'd have a take away 2i, and the take away 2i would be the imaginary part. With the other set of curly brackets, if you multiply out the brackets, you'd have z take away 1 and then plus 2i. The real part would be z take away 1. That's the real part. And the imaginary part would be that plus 2i. That's the bit with the i's. So you want to kind of write this so you've got the real part, an imaginary part, real part, and imaginary part. And when you multiply out the brackets, you're going to multiply the real part by the real part, then the real by the imaginary, then the imaginary by the real, and imaginary by the imaginary. So doing that, you'd have the z take away 1 times z take away 1. So that would give us z take away 1 all squared. We would have the z take away 1 times 2i, so we'd have z take away 1 in brackets multiplied by 2i. But then what we're doing is we're multiplying the negative 2i by z take away 1. So again, you'd have the z take away 1 times 2i, but it would be take away that. So really, they would cancel out. And then you've got the negative 2i times the plus 2i, which will give us take away 4i squared. Because we've got the brackets here, and because we've got the I squared, we can deal with them. So multiplying out the brackets, well, imagine that as z take away 1 times z take away 1. Let's multiply out the brackets here. You'd have z times z, which is z squared. We'd have take away z, take away z, which is take away 2z. And negative 1 times negative 1, if you wrote this with two brackets beside each other. So negative 1 times negative 1 would be plus 1. And then negative 4 times I squared is negative 1. So you'd have negative 4 times negative 1, which will give us this plus 4. Simplify that, and we've got z squared, we've got to take away 2z, and we've then got a plus 5. So what we've done is we've taken both of those factors, multiplied them together, and we've now got this quadratic factor. What we can do next then is we can take this z to the power of 4, take 6z cubed, blah blah blah, and we can write that as, in brackets, z squared take away 2z plus 5 times by something else. But how would we find that other bracket? What would we have to do? Well, we would have to factorise. And to factorise, we have to divide this. The z to the power of 4 takes 6z cubed, blah blah blah. We have to divide it by the z squared take away 2z plus 5. So, to do that, to divide it, you would have to use, perfect, you would use algebraic, long division. Bum bum bum. So, take the z to the power of 4, take 6z cubed, add 18z squared, take away 30z plus 25, and divide it by that larger quadratic factor that we found. So, to do that, just think back to lesson 1.4 when we learned about algebraic long division. Remember, I always think about Dracula must suck blood. So the D stands for divide, M is for multiply, S is for subtract, and B is for begin again. So D for divide first of all, and it's always the first terms that you divide. So z to the power of 4 divided by z squared, well, that's going to give us an answer of z squared, and our answers go at the top. We know that. So Dracula must, and must is for multiply. So we multiply the z squared by z squared. That will give us z to the power of 4. Z squared times negative 2z will give us take away 2z cubed. And z squared times 5 will give us plus 5z squared. After that, Dracula must suck. So subtract. So z to the power of 4 take away z to the power of 4 will give us 0. Z to the power of 4, they should always cancel out. If they don't, you have made a mistake. Negative 6z cubed, take away negative 2z cubed. Well, when you're taking away a negative, you would add, so that would give us negative 4z cubed. 18z squared, take away 5z squared. Negative 30z, take away 0. And 25, take away 0. From there, you have to, Dracula must suck blood, you begin again. And you begin again if the degree here is going to be equal to or larger than the first term. So here we've got a z cubed, here we've got a z squared, this is bigger, so we begin again. Dracula, you want to divide, so negative 4z cubed divided by z squared. If you divide them, well, you've got the negative 4 and you would have z, so that would be negative 4z if you divide that by that. After that, must for multiply, negative 4z times the z squared would give us negative 4z cubed. You should always be getting the same thing there. Negative 4z times negative 2z is plus 8z squared. And negative 4z times 5 would give us negative 20z. Dracula must suck. Subtract. So now you take away. So subtracting these two terms will always cancel out. Again, if you don't, you've made a mistake. 13z squared take away 8z squared is 5z squared. Negative 30z take away negative 20z. Two negatives, we come add, so that would be take away 10z, and 25 take away 0 is a 25. From there, again, Dracula must suck blood. B for begin again. Do you begin again? Yes, you do, because you've got a z squared here and a z squared. You have to keep going until the degree here is lower than what you're wanting to divide it by. So 5z squared divided by z squared, well, that just gives you 5. Again, the answer will go at the top. Must for multiply, so 5 times z squared is 5z squared. 5 times the negative 2z is take away 10z, and 5 times 5 gives you 25. After that, you want to subtract, so subtract 5z squared, take away 5z squared will give you 0, negative 10z, take away negative 10z will give you 0 again, and 25, take away 25 would give you 0. So we end up getting 0. But that's no surprise. We should be getting 0 at this stage because we know that the z squared take away 2z plus 5 is a factor of all of this. When it's a factor, we should be getting a remainder of 0. So we know then that our f of z, we can factorise all of this. We can factorise the z to the power of 4 take 6z cubed, blah, blah, blah. We can factorise that, and it would be, well, the first factor was the z squared take 2z add 5, and the other factor that we get is just our answer that's at the top. That is the z squared take away 4z plus 5. So factorising it, that's what we have. From there, though, we have to keep on going. Remember, we are wanting to find the roots. And the roots for this part we had, but we need to also get the roots for the z squared take away 4z plus 5. And to do that, well, how do you get the roots from here? What do you have to use? Brilliant! You have to use the quadratic formula once again. So, the remaining roots will come from the z squared take away 4z plus 5. So use a quadratic formula with a as 1, b as negative 4, and c as 5. So your quadratic formula, z would equal negative b plus or minus the square root of b squared minus 4ac over 2a. Sub in the values for a, b, and c. Dump. Simplify there, and you end up getting 4 plus or minus the square root of negative 4 over 2. Once again, you get the square root of a negative. What do you do when it's the square root of a negative? Well, you have to think about splitting that up. So imagine it's the square root of 4 times the square root of negative 1. Square root of 4 is 2, and the square root of negative 1 is I. Perfect. So you can say that would be 4 plus or minus 2i over 2. From here, because you are dividing by 2, divide both the 4 and the 2i by 2, and you'll get 2 plus or minus I. Meaning then the roots would be, well, right at the start we had z equals 1 plus 2i. We know the complex conjugate of that, the 1 take away 2i, was also a root, and what we did was all that hocus pocus, and we found that the final roots would be z equals, well, the 2 plus I, and also 2 take away I. And that would be all the roots of our equation. Woo! Try some of the questions in the Unit 3 booklet on pages 56 and 57, working out the complex roots of polynomial equations. Best of luck with that. Yeah. Have fun. See ya. Woo. Bye.